Welcome. This is Rust and C++ Cardiff/Dragons. This is our book club, Operating Systems, 3 Easy Pieces. We're covering chapters 6 to 8. If you missed the last chapters, they are available on YouTube. And the book itself is available online via the link. Last session, we looked at the concept of a process, which is the operating system's abstraction of running a program. And the operating system uses this abstraction to create the illusion of like an nearly endless supply of CPUs through this idea of virtualization. We haven't talked about what that is in detail yet, but the concept is there. In order to do that virtualization and creating this illusion of CPUs, we have to do some kind of context switching between processes in order to share time and memory. So you might take a process which is running, and then the operating system might choose to deschedule it and move it into this ready state so that it can run something else to do that kind of time sharing or memory sharing. It then might get scheduled again, start running, but maybe it then needs to do some kind of blocking operation, which will then move it into this blocked state while it's waiting for some kind of input. But once its I/O is done, it can then be moved back into the ready state, ready for the operating system to schedule it again. If the operating system schedules it again and it's able to run to completion, then that process might be able to complete. Dreamy. This is what that looks like. This is straight out of the book, but the previous diagram and this one are both straight out of the book. If you had two processes running, your first process might run to completion and your second process might then subsequently run to completion. Or if you were doing some kind of switching, you might be able to have a little bit of process one, a little bit of process two, etc. And the way it's achieving this, virtualization. So what is the point of virtualization? Why are we doing this? Mainly so that the operating system can prevent badly behaved programs from doing bad things. A badly behaved program doesn't necessarily mean malicious. It can also just be one that's got a bug in it. One that, accidentally loops forever, for example, is a very classic bug that people often write. In order to prevent badly behaved programs doing bad things, it has to be able to stop running processes to combat that very issue we talked about, where the process might just keep running indefinitely. But it also wants to do this in an efficient way. We don't want to add excessive overhead. We want our program to run fast. And we also want multiple applications to be able to complete in a timely and responsive manner. So in the previous example, we looked at just running process 1 to completion and then running process 2 to completion. But if we can do that deschedule schedule switch, then it means we can run multiple applications kind of interspersed together so that they can both kind of complete in a timely and responsive manner and not just queue them up. So these are the chapters that we're going to cover. This looks like a wall of text, but if you're looking at the OSEP book, you'll be able to then kind of cross-reference. We're going to cover one of the kind of simplest ideas, which is limited direct execution. We're then going to talk a little bit about switching between processes and how you might use different mechanisms for scheduling to do that. And then finally, we're going to look at a multi-level feedback queue to try and get like a much better scheduling model. So, limited direct execution. Throughout the book, there's these crux kind of highlighted blocks, so I'll be kind of showing those as is. The crux initially of this limited direct execution is how to efficiently virtualize the CPU while still maintaining control. So the operating system must virtualize the CPU in an efficient manner while maintaining control over the system. And this is going to require the hardware and operating system to work together. So if we want to run efficiently, one of the main ways you might do that is just by running it directly on the CPU. This is direct execution. Essentially, this is creating a process entry in the process list, which we talked about last session, allocating memory, loading the program code into memory from disk, locating the entry point like main, executing from then on, and letting it run to completion before returning. So far, so simple. But the problem there is we have no entry point in which to deschedule the running process because our operating system at that point is not running. It's not doing anything. Our program is running instead. This other process which has been kicked off by the operating system has now taken over the CPU. And that user's process could also do anything. So if we are allowing kind of arbitrary execution of code by this program, it could potentially blat over a load of stuff that our operating system is relying on, could completely trash our machine. So one of the ways we can try to mitigate that is by restricting the operations that these processes can run. So for example, we could block direct memory and IO access, and that will help to at least protect our, our operating system and the memory from the processes that are running. But, unsurprisingly, if you want to write a functioning program, you do need these kind of operations. You do need to be able to interact with memory. You do need IO access. You need to work with the hardware. Which brings us on to our new crux. How can we perform these restricted operations like IO without giving the process complete control over the system? And yeah, similar to what we were talking about a minute ago, this is going to require some input from the hardware, help from the hardware. This is where we get into this idea of user mode versus kernel mode, which you might have heard of. The idea is that your process, which is not the operating system, this is some other program that you're trying to run, is going to be operated in user mode. That means the hardware itself is going to block certain program operations like IO, like access to hardware, memory, files, etc. And it's going to mean that while that process is running, it's not going to be able to execute these operations. Whereas in kernel mode, the operating system is going to be, a program can do what it likes. So the operating system you can think of as like a set of programs that are operating in kernel, or might be operating in kernel mode. And that means that they can do these elevated privilege operations. And you can control this then with something like a mode bit or something equivalent that would only be able to be changed, crucially, when you're in kernel mode, because otherwise your user mode could just say, I want to be able to do that. I'll just switch on this option. But we still haven't given a way for our program to call these operations. And the way we can add that kind of functionality in is through this idea of syscalls. So the program is going to execute syscalls, which are going to pause the program, essentially, and switch to kernel mode in order to do these operations. And these are called trap instructions, or they're called different things in different places, but yeah, we're going to call them trap instructions. That's what the book calls them. I find the terminology around this a little bit confusing, so I was looking online to see like a nice summary, and I came across this one from Cornell University's notes. You can think of a trap as any kind of control transfer to the OS. So in our case, we started off in user mode, we have this program, we need to do something which our program is not allowed to do because it's in user mode. So it has to do something to execute a trap and transfer control to the OS. And the way it does this is using a syscall. Well, a syscall in x86, it might have a different name in different platforms, but essentially it amounts to the same thing. And that's not the only kind of trap. So syscall is something that you've deliberately chosen to do, but you might also transfer to the kernel or and it's something in kernel mode by throwing an exception. So like dividing by 0, page fault, etc. Or possibly there might be some kind of interrupt. So if you're waiting on a packet to arrive on a particular port, then there might be an interrupt when it arrives. And those are the kind of traps that exist. Some examples of system calls that you might see, so these are the ones that you've kind of chosen to do in your program, are printing a character to the screen, sending a packet on the network, allocating a page, sleeping. And the way these work, the program is going to execute a numbered system call. The hardware is going to save the process state and jump to the OS. It's going to check if the system call is valid, and that's not just necessarily the number, but also potentially additional data that goes with it. The OS will call the operation associated with that system call number, and then a return from trap instruction will reinstate the process where it left off by repopulating all the memory where it needs it, populating the registers. And this kind of set of instructions is going to be kind of listed out in something called a trap table, which will be populated when you boot the operating system in kernel mode kind of at startup time. And then the hardware is going to look at that trap table, remember the address of the syscall handler, so that it will then know which bit of code it needs to jump to depending on what syscall is executed. And in the book, if you're going through it, this is the very handy diagram that they have put together to show you how that looks in practice. So after you've initialized that trap table and you're actually running, your operating system might create an entry for a process. It's going to allocate the memory for the program. This is what we talked through earlier. Load the program into memory, set up the user stack, fill the kernel stack, and then we'll return from trap, which essentially means we're then going to go to the hardware, which is going to restore the registers from the kernel stack, move to user mode, and then jump to main. And now the program itself can now run. If it needs to do a system call at this point, that's when it traps into the OS. And as mentioned, the hardware at that point will save everything off to the kernel stack, so essentially suspending the program, and move to kernel mode and jump to the trap handler, which it knows where it is because of the trap table. This will then handle the trap, do the work of the syscalls because it's got those elevated permissions because it's in kernel mode, and then we'll execute return from trap so that it can then kick off the program again. The hardware sees that return from trap, restores the registers from the kernel stack, moves it to user mode, and then kicks off the program, return from main. When we finish, it's another trap, but this time we're just exiting. Our process is done. The operating system can now free the memory, remove from the process list. Everyone's happy. And as mentioned, in different architectures, this might look slightly different, but it amounts to the same thing. So I took this diagram from the ARM website, and their version of like syscall here is supervisor call. They also have like hypervisor call and other ones because they've got different like levels of permissions. They don't just have kernel mode and user mode. But essentially this amounts to the same thing. You've got your application, which is going to try and execute a supervisor call. The supervisor call handler is then going to look up what it needs to, where it needs to jump to, based on the operating system's vector table of all of the possible syscalls that it has. Yeah, and again, it's that similar kind of loop that then allows it to do these privileged state operations, equivalent of like kernel mode from the previous diagram, without letting the application actually do it directly itself. And that means the operating system can put in other checks and balances at that point to make sure that it's not trying to access memory. It shouldn't, that it can, essentially just make these operations that little bit safer. And it introduced obviously a small amount of overhead to do this, but not like inordinate amounts, and very much worthwhile compared to running a program and just trusting it blindly. So let's go back to what we talked about earlier with virtualization. The first one of these is the operating system must prevent badly behaved programs from doing bad things. We have done this to a degree by putting the operating system in between. We have allowed us to still do these restricted mode operations, but we're doing them with a level of indirection so that we can protect our operating system and protect our machine from memory access that would allow a program to just like blat over everything or read all of your memory and do what it wants with it. But we haven't done the other parts here. So with this current kind of mode, we're relying on the program executing a syscall in order to hand control back to the operating system. If it doesn't execute a syscall, then the operating system is still just sitting idle, not running. And so the process can still keep running indefinitely. The operating system with our current model is not able to stop a running process. So another crux. This time, the crux is how to regain control of the CPU. So the operating system needs to regain control of the CPU so that it can switch between processes, so that we can achieve that aim that we were looking at the start, where we can have processes being scheduled and descheduled so that we can switch things in and out. As mentioned, with system calls, we are getting that control back to the operating system. So at that point, if we wanted, we could deschedule the task because we as the operating system at that point have control. But we're relying on the program having actually done a system call. And this is called cooperative scheduling. It's this idea that like we assume that all of the programs that we're running as our processes are well behaved and will do system calls or will yield regularly with other trap calls back to the operating system to allow us to switch things in and out. You might think that doesn't sound very useful, but actually this is what a lot of operating systems used to do. So classic Mac OS used to just rely on cooperative scheduling. which you can do when everyone's on the same team trying to make their programs run well, and when there's not as many people producing programs, so you can maybe call up the person who's broken it and say, why is this program not yielding? It's been running for 10 hours, and then people can fix those bugs. Windows pre-95 also had cooperative scheduling along with a whole host of other things. It's also kind of, in essence, the way async behaves. You're essentially relying on yield points in your code to be able to schedule things sensibly. But if you had just a super CPU-bound task in like an async workload, nothing else is going to get scheduled while that CPU-heavy task is going unless you yield back to the runtime to make those choices. So yeah, this relies on, to do cooperative scheduling, you're relying on programs being well-behaved. But what if it isn't, not just malicious, maybe just a mistake? You could just reboot your machine, fix your code, rerun it. That doesn't work all the time. It also means it's going to be very annoying. And yeah, it isn't necessarily going to help you. So we need a better way. And one of those better ways, kind of the main better way, is using the hardware. So the hardware can do things while the process is still running. And so we can introduce the idea of a timer interrupt, which is a hardware operation which allows the hardware to suspend the process, just like it did at the point at which we executed a trap instruction, where it kind of stored things off and then handed control back to the OS. We don't have to wait for a syscall now. We have to wait for these trap instructions. We can, arguably this is a trap instruction, but it's that third type. So rather than it being a syscall, it's an interrupt. It's a new type of trap which returns back to the kernel. So the hardware suspends the process, and the frequency with which it's going to be doing this will be set up by the operating system. So the OS will set up the interrupt handler. The OS timer interrupt handler is the thing that is going to be executed. So, so when the hardware suspends the process, it needs to know, like, okay, I've done this timer interrupt. What do I do now? It's going to look in the trap table that it set up, and it's going to find the interrupt handler and say, this is what I do when the timer interrupt handler kicks off. And then the operating system decides what happens next. So at that point, you can deschedule your process, or you could schedule it to run again, or you could do something else. This is a kind of context switch. So you're taking the process memory and you're packaging it up in the kernel stack, potentially swapping it out for something else if you choose to switch in a different process. That is not free, but it does give you that control. And again, handy diagram from the book here. The operating system at boot mode, like we said, initializes the trap table. So now we've got two handlers to remember, multiple handlers, many handlers, but remembering the addresses of the syscall handlers for the many different types of syscalls and the timer handler. So I'm going to start the interrupt timer. The hardware is going to start that timer, and it's going to say, okay, I'm going to interrupt the CPU in this many milliseconds. And that means then when the application's running, so in this section here, process A is running. After the timer interrupt executes, it's going to save the registers into the kernel stack, move to kernel mode, jump to the trap handler. The trap handler here is going to look at the timer handler, and the operating system is now going to have control. At this point, we could choose to switch out process A for process B so that we're giving different processes a fair amount of time to run. So in this case, they're calling switch routine, saving registers A, and then restoring the registers associated with B, which might be empty at this point. Like, we might not have done anything with process B yet. It might be the first time it's being run. And then switch to the kernel stack and return from trap into B. The kernel is then going to restore the registers into the kernel stack, move to user mode, and jump to process B. So again, this is this context switch. Process A, kernel registers have been explicitly saved by the operating system into memory. process B is registered are restored from the return before the return from trap. So this is the kind of slightly more expensive bit. If you just restored process A, it would be slightly cheaper because you wouldn't have to do this explicit store by the OS into memory. You'd just be able to, you would still have the kernel registers kind of populated, and then the kernel would be doing it. It would still be a cost, but it wouldn't be as much. Switching the processes is going to be slightly more of a cost. In future chapters, we're also going to have a think about how concurrency might interplay with this. So we've talked about like this kind of one track going through, where when you're doing an interrupt, you're dealing with that interrupt. But what happens if another interrupt comes in? So it could be that the timer happens during a syscall. What happens at that point? Do you execute the syscall, or do you, switch to the interrupt handler? And that will be covered in future chapters. So let's go back now with our new tool, the interrupt handler in our pocket and the timer, and see how we're doing on virtualization. So we've already said we're preventing badly behaved programs from doing bad things, but now we are also able to stop a running process using these timers. Are we adding excessive overhead? We're adding a bit in terms of the context switching, potentially, but we don't have to do that. And it's not going to be hopefully impacting our program's ability to run quite fast. But that will depend again on how frequently you're checking this timer. How quick, how long are you going to let your process run for before you interrupt it? Because each one of those interrupts is going to have a cost. Have we completed this last step in virtualization, where we want multiple applications to be able to complete in a timely and responsive manner? Maybe we have. It's unclear at this point. To do that, to figure out if we've done this, we need to kind of define what it means for something to complete in a timely and responsive manner, which is the topic of the next chapter, chapter 7, scheduling. The crux of this section is developing a scheduling policy. So how should we develop a basic framework for thinking about scheduling policies? What are the assumptions? What metrics are important? What basic approaches have been used in the earliest computer systems? So the goal, as we had earlier on our virtualization list, is we want multiple applications to be able to complete in a timely and responsive manner. The easiest kind of initial simple metric we can use here is the idea of turnaround time. So from when we start a task, so T arrival, to when it completes, how long is that taking? And we're going to call this the turnaround time. There are a series of like simplifications or assumptions or simplifying assumptions that you can make to start to think about this. First one might be, let's assume that each job runs for the same amount of time, that all the jobs arrive at the same time, and that once started, they run to completion. So we're going to forget about all those syscalls nonsense. Let's also assume that all jobs only use the CPU, which is going to be kind of necessary to run to completion, not necessarily, and that the runtime of each job is known. That last one is obviously often an unreasonable expectation of a program. But with those assumptions, we can now start to reason about them. So let's take the example of 3 jobs arriving in the system, A, B, and C, at roughly the same time, each taking 10 milliseconds. This is what that might look like if we did a first in, first out type model. So they've arrived at the same time, but something's got to arrive ever so slightly first. Let's say A arrives first, we run it to completion. Then B, run to completion. Then C, we run to completion. The turnaround time, because they all arrived at the same time, the turnaround time there is just going to be the completion time. The first one finished after 10 milliseconds, the second one finished after 20 milliseconds, and the third one after 30, because they each took 10. So this is a turnaround time averaging of about 20 milliseconds, I think, for our units, more 20 something. But what if we do away with that initial simplification? What if these jobs don't run for the same amount of time? So let's say that the third one, C, takes 100 milliseconds. Again, all of them are arriving at roughly the same time. But now suddenly you could end up with sorry, that's the wrong way around. A is taking 100 milliseconds. You could end up with this kind of slightly like pathological case where your longest process might be getting in first, You've kicked it off, and now your other two are just waiting there, even though they would have been done really quickly. They would have been in and out in 10 milliseconds. But in this kind of worst case scenario, the turnaround time is going to be 100 for that first long running task, then 110, then 120, because they all took they all had to wait for that first process to complete, which means our turnaround time is going to be averaging about 110 units, milliseconds, say. Whereas if we had been able to switch around the order, then we could have completed the first two tasks within the first 20 milliseconds and then run the last one. And that would have given our average turnaround time of 50 milliseconds, which by our metric that we have chosen would be a much improved state of affairs. So how can we do that in a kind of consistent way rather than just randomly switching the orders until we get a nice time? We can do the shortest job first. So in our case of A taking 100 milliseconds and then B and C taking 10, if they all arrive at roughly the same time, when they arrive, we're then going to look at how long those jobs are going to take, and we're going to sort them in order. So the shortest job runs first. Now we've got that ideal case for these three where the best turnaround time we can get is going to be this averaging of 50. But what if they didn't all arrive at the same time? What if we get rid of that simplification as well? Now suddenly we have to take into account B and C potentially arriving after A has already kicked off, which essentially means we're back to the almost pathological case where B and C are having to wait all this time until A has completed. To deal with that, we're going to need to get rid of simplification number 3. So each job running to completion, because if each job's running to completion, there's no way we can, beat that previous turnaround time, because A started, and at the time A started, we didn't know about B and C, so we didn't know we had to wait for them. But if we don't run the jobs to completion, then it means we can instead try and optimize for time to completion. So we can look at the time to completion for each of those tasks instead to decide what we should be running instead. So at any point in time, we would look at the jobs that are there, determine which of the remaining jobs has the least time left, and then schedule that next after interrupts. So what that would look, this is called preemptive scheduling. So we're looking at the shortest time to completion first, and that's going to require us stopping a task midway through if there are other tasks that need to run, which would complete sooner. This is also called preemptive shortest job first scheduling. So this is what that might look like. So we've taken task A, which has started. When B, C arrive, we reevaluate the jobs we've got left. A at this point still has 90 seconds on the, we know how long it's got left. It's got 90 milliseconds or 90 units. B only has 10, C only has 10. So now we know, okay, we need to stop process A, we need to suspend it, and then we need to kind of replace it with process B, run process B to completion, then make the same judgment call, which is going to complete faster, C or A. Still got 90 on A, 10 on C, so we're going to run C, and then finally we'll go back to running A. So we have now looked at the shortest time to completion rather than just allowing each of them to run once they've been kicked off. And this has gotten us back to a much better turnaround time. But turnaround time isn't the only thing we care about. You might also need some kind of interactive performance. So if you are working on a computer, you might expect your mouse to move, for example, or you might expect, something to respond to what you're doing. You also might just want to know that things are working. You might want to see that processes are running so that you know that they're working. So there's this requirement for interactive performance, and we can optimize this by optimizing for responsiveness rather than turnaround. And it's this idea that we want everything to seem like it's running, to have done something. So this is going to be measured by the time it was first run minus the arrival time. So we only care about the first time it does something. We want all of our applications to do something relatively quickly. So in terms of response time, going back to our first in, first out example, now process B isn't going to start until it's already 10 milliseconds after arrival time, and process C isn't going to start until it's 20 milliseconds after arrival time, which means our response time here is coming out at 20, which is maybe fine, but for these processes being longer, it might not be. To optimize for that, we can instead switch our processes in and out. We're going to do this via a simple round robin approach, which means that we run our job for a time slice and then switch in another process. So instead of doing this kind of run process A, then process B, then process C, we're instead going to do a little bit of A, a little bit of B, a little bit of C. And you can see, depending on how short I made those time slices, the time to initial response is going to be like arbitrarily small. So it'll be like 1 time slice for the first one, 0 time slice for the first one, 1 time slice for the second one, 2 time slices for the second one. So if you condense these down, you can get a good initial response time. Doesn't mean it's necessarily going to be optimizing for our turnaround time now, but we will be optimizing for response time. You can think of this as being more fair because everything's kind of looking roughly equal. You're kind of just switching in and out, doing a bit of one, bit of the other, bit of one, bit of the other. But it is going to be worse for turnaround time because if we look at this diagram, you can see none of A, B, or C have completed by this point here. They're all completing around the end time. Nothing's completing quickly. And there's also a lot of context switching, and we've said context switching is not free. So there's going to potentially be a performance hit that we are incurring there, depending on how small we make those time slices. We can complicate the problem further by considering the fact that programs and processes often want to perform I/O. So they're not only doing CPU-bound tasks. If we eliminate that assumption, then we have to incorporate another factor, which is the fact that we don't need CPU when we're waiting on I/O. So there's no point the process just sitting there waiting. Other work could be scheduled while you're waiting and you wouldn't make things any slower. So for example, if we had 2 jobs or processes, job A and B, and they both need 50 milliseconds of CPU time to run, but job A also does some kind of I/O request every 10 milliseconds, which involves waiting for 10 milliseconds, then you might end up with something like this. So if our process A was allowed to just run a bit and then was blocking, waiting on some I/O operation, like waiting on reading from disk, then there's this dead CPU time that we're not doing anything with. If we didn't schedule B at that point, which we wouldn't necessarily with our models so far, because when you look at like the actual CPU time left, it's comparable, so that you wouldn't necessarily think that you could switch in B at this point. But if you did switch in B, you could finish much quicker because these kind of time slices here where we're waiting on disk, we're not doing anything. The CPU is idle. So we've eliminated 4 of our simplifications/assumptions. Now we need to get rid of the last one. The runtime of each job is known. Normally, the runtime of your applications is not known. You don't know how long things are going to take, which means all of our models so far for doing sensible scheduling rely on us knowing which ones are going to complete quickly. And we just simply don't know that at the start of processes run. And that is why we need something a bit smarter, which is covered in chapter 8 in the form of a multi-level feedback queue. Any questions about what we've covered so far before we move on to multi-level feedback queue? No? Good. I will plow on. The crux of the multi-level feedback queue is how can we schedule without perfect knowledge of the system? So we've been optimizing based on how long we think these processes are going to take to run. But if we don't know that, how can we schedule it to minimize response time for interactive jobs and turnaround time without knowing anything about the processes that we're running? The multi-level feedback queue assigns a priority to each job. This is the way it chooses to tackle this. So without knowing anything about the job, it just assigns a priority. Among these jobs, if the priority of A is greater than B, it's going to run A. If the priority of A is equal to B, then it's going to run them in round robin. But that priority, we need to figure out how we're going to actually assign it to a job because we don't know anything about the processes when we start them. But as we run the programs, we're going to learn something about how they behave, and we're going to update those priorities based on how the process is behaving. We're going to allot an amount of time that each job is going to spend at a given priority level. And when we say time, it's going to be like CPU time. And when a job enters the system, before we know anything about that job, we are going to put it at the highest priority. We're going to say, this is a new process, it's going to run. This is our most important one. And if there's other processes that are also at that top level priority, they'll just be round robining. If a job uses up its allotment of CPU time, then it's going to have its priority reduced. But if a job gives up the CPU before the allotment is up, so by doing like an IO operation, we're going to reset its allotment. We're going to keep it at the same priority level in order to try and keep it responsive because it's doing IO things. This essentially means that if a job's running for a long time, or if its CPU is running for a long time, then its priority is going to drop. But if it completes quickly, it's not going to drop in that time, so it'll stay high priority and it'll get run to completion, which should be good for turnaround time. The problem with this approach is that we have added in this third case of if the job gives up the CPU to do IO, we're going to reset its allotment. And if you're a malicious actor or you just want more time on the CPU, you can game this. You can game this by never letting your allotment run out, by always doing an IO operation just before it runs out, so that you can then stay in your high priority queue. So essentially, you're kind of being unfairly kept at the top of the queue, which can lead to then other things not getting scheduled. So CPU heavy jobs might be starved of resource because every time they run, they get dropped lower and lower and lower down this priority queue. And when they're at the bottom of the queue, like if there's loads of processes above them and those ones are doing IO, so they're never dropping down, then you might not get scheduled. So to combat that, we're going to add in a new rule. After some time passes, we're going to take all the jobs in the system and we're going to move them back to the top of the queue. And that way, the kind of CPU-bound tasks that have been shuffled right back down to the bottom of the priority queue are going to, at least after this time period, go back up to the top and be round-robined with everything else. This means that our jobs are no longer going to be starved. There'll be nothing that's going to sit down at the bottom of the queue indefinitely. And that also means that if we had a CPU-bound task which suddenly needs to wait on some IO, or it's like done its CPU-bound stuff, it's no longer CPU-bound, now it just needs to do interactive things like reading and writing to disk or looking at ports or interacting with other hardware, it will now be in this kind of more interactive state and it will be able to stay in that bumped higher priority because we elevated it there after this time period, and it will no longer drop down because it's not doing the CPU heavy things anymore. So this is what that might look like. If you didn't do any kind of priority boost, then our process, which is like heavily CPU bound, is going to run for a little bit of time at the top of the queue. Then it's going to get dropped down because it'll have used its allotment. Run a little bit of time in a lower queue, drop down again because it's used its CPU allotment. And then it's going to sit in the bottom of the queue. And if nothing else is running, then that's fine because it will just run even though it's at the bottom of the queue because there's nothing else higher in the queue. But as soon as you bring in another task, which is going to, when it enters, be at in the highest queue, suddenly our CPU bound task that's at the bottom of the queue is not going to get scheduled. And if the new task that's entered the conversation is IO bound, then or not even just necessarily IO bound, but it's doing IO requests in under the time that it's doing the allotment, the more frequently than it's deprecating its allotment of CPU time, then you're going to end up with something like this, where it's doing a bit of CPU time, maybe waiting, a bit of CPU time, maybe waiting, and it's resetting. So even though when you look at the CPU time that it's actually spending, it's spending just as long as our our fully CPU process was running for, it's now basically the only thing getting scheduled because this one here is going to stay lower down in the priority queue. If instead we bump it up after our time zone, so we've done this priority boost, Now suddenly it's going to get elevated again, which is then going to allow it to like run for its time slice. This avoids the ability to game the system. Sorry, this doesn't avoid the ability to game the system. What this does is it stops things being starved of CPU resource. We still need to find some way of preventing things from gaming the system. The way we're going to prevent it from these things doing IO requests just before its CPU time allotment runs out is we're going to no longer reset that allotment after an IO call. We're going to keep track of that CPU time across the IO calls of a job, and then that way it will still get dropped down in priority. Save on the assumption that it will get bumped up again. It'll get this priority boost the same way that everything gets this priority boost after a certain amount of time. And there's loads of considerations that you can look at here when you're doing priority boosts. You can change the number of queues. The previous example we were looking at just had 3. You can also change the time slice per queue. So maybe if you're in Q2, you've got this allotment and you're not going to drop down to Q3 until you use up like twice as much as you would if you were going from Q3 to Q2 or something. So you can change the time slice per queue. You can change the allotment. You can change the boosting algorithm to avoid starvation. So maybe you don't boost it all the way to the top. Maybe you just boost it up 1 level. Maybe you boost it up 2 levels. There's a bunch of different kind of things you can alter here to try and get a system which is going to be well balanced. And in the book, they talk a bit about kind of like these magic numbers and the fact that it's a little bit of an art form figuring out what numbers of time slice per queue, allotment, how long before you boost things, how high to boost things to get the best out of your system. Obviously, the more you know about the system and the more you kind of know what it's going to be used for, the easier it's going to be to decide on what values to set here. We're trying to balance good response and completion time of interactive and short processes without starving CPU hungry tasks. And I think we have kind of achieved that with this process of boosting and time slicing and kind of dropping things down in the priority queue. And it's relatively simple. The diagrams not necessarily the easiest to read, but the concepts there are quite simple when you're just flowing through it. So to summarize, the way this multi-level feedback queue is working is it's giving things a priority. It's going to run things based on their priority. If the priority of job A is higher than priority of job B, it's going to run A. If they're the same, it's going to round robin them using the time slice of the queue, and that can vary by queue. So in if you're lower down in the queue, then you might give things longer because they're more likely to be CPU bound. When a new job enters the system, we're going to put it into the highest priority to give it a chance to run, and maybe it will complete quickly and then it'll be out of our queue and we don't have to worry about it. Once a job uses up its time allotment at a given level, regardless of how many times it's given up the CPU to IO, its priority is going to be reduced. So it's going to move down a queue, and that's to prevent that gaming of the system. And then after time period of S, we're going to move all the jobs up to the topmost queue in order to account for the fact that they might have changed their behavior and to give tasks a chance to run, because they will definitely be round robined if they're back at the topmost queue because they'll all be at the same level. So that's chapters 6, 7, and 8. Essentially, it kind of boils down to this. The hardware is providing tools that allow us to balance process performance while not losing the operating system's control. The operating system's control given to us by the hardware tools means that the operating system can schedule workloads efficiently, and we do that by dynamically queuing jobs to balance performance and fairness to make sure that things can keep running, but still also maintain kind of that interactive nature. And that's those chapters. That was a whistle-stop tour. I hope it made sense. Apologies for the various mistakes and hiccups along the way.
Yeah,
Any questions?
very nice.
Do my best to answer.
Very nice, thank you.
I guess not really a question, but an observation I made earlier was that this delineation of traps being composed of system calls, exceptions, and interrupts was something novel to me when kind of going through this, and I think it's very nice to think of it in that kind of three-way trichotomy. Um,
Definitely. And it seems like it's not like necessarily universally agreed to use those words in that way, but it's the way that made the most sense. And yeah, I think it's
mhm.
the clearest. It seems to most fit most people's definitions of yeah, of a trap call. That those ones are from this. I can drop those links in the chat. Let me just oh, strong feeling these slides were made with types. You are correct. My first time using types. I liked it. It was good. Yeah, normally use MARP for markdown slides, which I'm still a big fan of because I think it's easy to read the content to yourself after the fact. I think with types you need to kind of have the rendered form next to it always to yeah, to
Hmm.
get the best out of it. But yeah, I'm a convert. I like it.
Nice, good,
The
good,
export
good,
to
good.
HTML was not good though.
Oh
It
yeah, I think
not
that's
does not
very
work.
under construction still.
Yeah. Let me get those links. So, exit presenter mode. All right, this is.
Yeah, for me too, like the most funny part was trap, because I was always imagining this corporate executives thinking about like in the 90s, what should we do? We get programs from the internet.
Hmm.
And then they came up with, we have to trap them.
Yeah. I feel like there's so many fun names in like especially in the like the older days of computing, like that we have different names for now. Like I remember in the previous chapters, like reading through this, there was some mention of like what operating systems like what they used to be. And so like there are some what were essentially primitive operating systems that were instead called the master control program. Um, which is like well, yeah that's real like military type domineering like you will be doing this or uh executives like so like the kind of inverse of an executable, like an executive is the thing that controls the executables. um so yeah, I think there's a whole gold mine of reading old uh kind of system software stuff.
Also kind of makes you realize that the words we've ended up with do sort of make sense because like operating system to me just is an operating system. Like it doesn't really, I
Hmm.
forget that it's the words operating and system.
Yes,
It's a
yes, yeah, yeah.
system for operating, for doing something. Um,
Mhm. Yeah, I definitely do like the sort of this more descriptive style, like not like the software we have nowadays that will like is usually has some like cute but meaningless name. Um, I have a taste for the weird and sort of the weird and wonderful. Um,
you just have to trust that the word is going to become so like
mhm.
ubiquitous that it won't matter that it's a weird combination of two words.
Yeah, like I would absolutely take like the container control program over Docker. That would be so much cooler.
But you know, they just call it CCP, and then it would be one
Yeah,
of
yeah.
many
Yes,
initialisms in the
yes.
world. Yeah, so there's lots more of the book to go. I will try and be quicker at uploading the recording this time, and Tim has kindly agreed to take the next few chapters. So I'll get the meetup event for that this week so that people know it's happening rather than being given no notice.
Mhm. And when is the next meeting planned?
It is going to be, all being well, the
in 3 weeks,
26th
I
of
think.
August.
26. Okay.
And so the question,
And
are you
the
completing the
PSL
book?
question.
That's the
That's the
hope.
plan.
We reserve the right to bail out partway through if if the mood is, if people feel like they've gotten everything they wanted from it, particularly because the concurrency chapters we've covered a lot in, not in operating system context so much, but we have covered a lot of the topics before. So if we find that it's not adding value for enough people, then we might bail out. But yeah, as long as there is interest, we will keep doing chapters.
Yes, and part of it, at least for me, is my own interest in having a reason to read the book. So that's pretty good.
Completely. I would highly recommend if anyone's thinking of volunteering to a chapter, I would really recommend it. You get a lot more out of it, I think, if you get, because you read it multiple times then. Like you end up reading it once just to be like, what am I going to be presenting on? And then you could read it again with like being like, okay, how am I going to present this? What am I going to add? It also encourages you to be like, when you get to a thing where you're like, I don't feel comfortable with the definition of this. So for me, that was, trap. I was like, when did they introduce this word? I went back through the previous chapters. I was like, they haven't really introduced it. Then I haven't really given it, they've kind of vaguely said what it is. And I still end up with a relatively vague definition, but it's not, it's, any control transfer to the OS. I was like, I can deal with that. That makes sense. And then here are the types. Yeah, so it helps you find other resources and, out of necessity, because people are going to ask you. Cool. Right, well, we're bang on time, which is good. So
All right. Thank you very much.
see you all in a few weeks.
Same
See you in a
here,
few
Ciara.
weeks.
Yeah. So yeah.
See ya.